in there. If not, you're going to put this where you take notes. Is that we're going to talk about modeling the data. So we've done this before. We enter data. We run regressions. We use our scatter plot, the shape of it, and some different information that we get from the calculator to determine if our model is good for the data and how good it is and if it's useful in other circumstances. They're going to amp it up a little bit with some of the vocab words and some of the other things that we're using. So with linear regression, we looked at an R value. What was the R value called? Like, what was its actual name? It said R equals, and it gave you a number, but R had a name. There's a vocabulary term that R represents. So on your test, I didn't say, explain what R means. I said, explain what the blank means. So what was R? It wasn't a root. The word actually doesn't start with R. No. So what does R tell you about your model? Soraya. How well your model fits the data on a scale of 0 to 1, right? So we call that correlation. We got no new seats. I think you're right there. So we call that correlation. So we called the R value the correlation coefficient. We only looked at that with linear data. Then when you guys started running quadratic regression, you noticed that the R value didn't come up by itself. Instead, there was an R squared value, okay? We kind of didn't pay that much attention to it, all right? It does have to do with the R value and then squaring it, okay? But basically, we want to come up with more formal definitions for what that is and what these two words up here are, interpolation and extrapolation. So what I'm going to do is give you guys a few minutes with your new group members to do a couple of things. You can use electronic devices to Google or go to some website you find useful. You can use textbooks. You can use any other information you have. And your job as a group is to come up with what you think these three things mean, okay? What does R squared represent? What does the word interpolation mean? And what does the word extrapolation mean? And this is all in the sense of looking at data for models, okay? So you guys have a few minutes. If you don't know the people at your group, ask them what their name is so you guys can share information and you're not doing everything individually. All right, so up here, we have a couple things written about R squared. It says a fraction between 0 and 1 that has no units, and X will not help predict the Y value. And then we have correlation, tells us how accurate our line of regression is. Okay. All right, so from group 8, let's see, person number D, Damien. Okay, so some stuff up here to help you, okay? So explain to them, if you were tutoring them, what R squared is telling them.
R squared is telling us if the line is either going to be accurate or less accurate. If it's closer to 1, it's accurate, and if it's not closer to 1, it's not accurate.
Good. Okay, so the closer the number is to 1, the more accurate, the further away, less accurate. Before, it wasn't R squared, though, right? Before, we just used R. So here's what mathematicians do. If you square something that's smaller than 1, what happens to that number? Does it make it bigger or smaller? Smaller, okay? So what they're doing is they're giving themselves an extra cushion because of error, because it's data, right? And you're just kind of estimating some things. And so R was a good value, but they're like, you know what? Let's square it. If it's still close to 1, then this must be really good model of this data. If it's not close to 1, I don't really know. But I've given myself an extra cushion by taking that extra mile and squaring it. For example, if you took 0.9999, okay, if that was an R value, and you squared it, somebody tell me, what do you get? Okay, you get 0.9998 for your R squared value. So is R squared still really close to 1? Yes, it's smaller than R, right? but still it's really close to 1. But if, let's say, my R value was 0.75, and you think like, oh, that's pretty good. Let's say you square that. What do we get when we square 0.75? What would you say about that? Not that great, right? So all the mathematician doing is giving themselves an extra cushion. The R squared value is not going to be good unless the R value was stellar, okay? So it's just giving them an extra way to err. They're not going to say a data set is good unless it's really good. Does that make sense to everybody? Okay, but the same rule applies. It's just kind of like rating something on a scale of 0 to 1. How good is it? The closer to 1, the closer it is to perfect. The closer to 0, kind of the worse it is to represent our data. Okay? But then we also have to actually look at our data. All right. Thank you, Damien, for being put on the spot and answering the question for us. All right. From group 3 to 2. Kyle. All right. So tell us about interpolation. Okay. So we're putting the points on the graph, and we're seeing how well they fit the regression. Now, the regression doesn't have to be linear anymore. We've done linear, we've done quadratic, and now we're going to move into even more. Okay? So he's right. It is looking at data on the graph and seeing how well, okay, your regression fits it. But what's the difference like between interpolation and extrapolation? Can anybody add to what he said? Damien already spoke to us. I know that he's got it. Are you guys going to make me pick someone else? There's a random integer selector on the calculator. So from group 2, person 1, Sophia. All right. So can you tell us maybe the difference between interpolation versus extrapolation? So in both cases, you put this data on the thing, right? You run some sort of regression. You have your correlation to look at. And so you're looking at it. But in one sense, you could be doing this. In another sense, you could be doing this. What's the difference between?
Interpolation is more like using like data and like facts, or well, they both use facts, but it's more like you have a method of doing it.
Okay.
Extrapolation is just like an educated guess.
Okay, fair enough. So extrapolation is more like a guess. Anybody want to add to what she's saying? So if we're looking at a set of data, okay, let's say you get a data set. Okay, it looks something like this. Do you think we should run a linear regression, a quadratic regression? What do you guys think? Linear, okay. Is the correlation positive or negative if it's linear? Positive. Strong or weak? Pretty strong. Okay, so you run some sort of linear regression and you get this line. It goes forever in this direction, forever in this direction, right? Anything that you use this line to calculate that's from here to here in the domain would be interpolation because you're using your linear model, but you're only using it within the numbers that you actually had data sets for. However, if I use the information to predict something way out here, was there any data that corresponded to points way out here? No. That doesn't mean I can't use this model to predict. I can follow the line and predict something that would happen out here. But that's considered extrapolation because I'm going beyond just where the data was and just kind of saying this trend would continue. So I'm going to keep using this model way beyond the data to make a prediction. So predictions that you make based on your model, your equation, but you're using x values that are within the data set. Okay, so if this was like from 3 to 10, anytime you plug in a number into your equation from 3 to 10 to figure out where this point is on your model, that's interpolation. Okay? To do the same thing but beyond 10 is extrapolation because there was no data there. I'm just kind of making an assumption that the model would continue. Sometimes that's a fair assumption to make, and sometimes it's not. You have to be a critical thinker about the situation. Like in this situation, can I use this model to extrapolate or no? Okay? And in some situations, you're like, yeah, it's going to keep growing over years or time or whatever it is I'm looking at. And in other situations, you're like, I don't really know about that. It could dip down or do some other things. I'm only going to use it within this interpolation area. Does that help clarify a little bit for people? Okay, so interpolation and extrapolation are both gathering information from your model, but one is in the same area where the data was, and one is beyond where the data was. Okay? All right, anything the cubic regression definitely gave an R-squared value that was much closer to 1 than in the other cases. What else would you use to back up your decision? It can't solely be based on the R-squared value. I can give you data and totally trick you. I can give you data that if you run a linear regression on, the R-squared value is 1, it's perfect, and the data looks nothing like the line that you get. Okay? So we can't just base it on that. All right? Okay, so if you looked at the graph, right, you saw that the line wasn't bad. It was going in the right general direction. The quadratic wasn't that bad, except for that the data tended to look like it was taking another turn and the quadratic didn't turn again. And then when you ran the cubic, it went through every point almost perfectly, and it mimicked all the fluctuations of the data, right? It seemed to turn everywhere the data turned. So we really want to make our case in order to give a thorough explanation of why a certain model fits data. We want to cite mathematically the correlation and what we know about that. But then we also want to cite what we're seeing in the scatter plot and our observation with how the graph fits. Those two things work together. We can't depend solely on one. We're not calculating enough to make a judgment of how good a model is. The calculator is not smart enough to observe data. It can only give you numbers to interpret. So we need to make sure that we look at both. Okay? All right, so we're going to run a second set of data. So we just talked about which equation you would use and why. All right, so some of you don't have the note-taking guide, so I'm going to put up the data. We'll talk about how we're going to enter it, and then we'll talk about the questions. So first, just look at what the questions are going to ask you. One says, what's the linear model that best fits the data? Use the model to estimate egg consumption in 1995. Okay. Question for you guys, before we even did any work. If you're going to use your model to predict egg consumption in 1995, is that interpolation or extrapolation based on this data? Interpolation. 1995 is a year within the years that the data was collected. So though you're using your own model to estimate what it would be, it's within the data that's there. Okay, so that's interpolation, not extrapolation. Okay? All right, the next question is going to ask you to run a quadratic model and to estimate egg consumption in 1995 using that model. And then the third question is going to say, which one do you think is better to model between 1970 and 2000? What are we looking at when we're looking at between 1970 and 2000? Interpolation, because that's when our data was taken. And then it says, which one do you think is better for extrapolating beyond 2000? Okay? If you had to choose one to guess what egg consumption is going to be in 2020, would you use the linear one or would you use the quadratic one? And that decision is going to be built on a few things. Looking at the scatter plot with how well the different regressions fit the data, looking at the R-squared values for those data, but then also some common sense and critical thinking about egg consumption, how fast that could possibly rise, different things like that. There are some other aspects besides just the numbers when you're looking at data. Okay? So basically, you are going to take this data, you're going to run a linear regression, you're going to run a quadratic regression, you're going to estimate both for 1995, and then you're going to state which one's better for interpolation and which one's better for extrapolation. Does that make sense to everybody? Okay. So question for you, how do we want to enter this data? Do you guys want to enter 1970, 1980, 1990, 2000? You can if you want, okay, but you don't have to. What's another way we could enter this data? Zeke?
Use 1970 as 0.
Okay, sure. So we could use 1970 as 0. And so then our X list would be 0 and then 10, 20, 30, and then years would depend upon that. Okay? So you can decide. Your group should be consistent if you want to compare equations, because obviously the equations would be different if you're plugging in different numbers. But the egg consumption approximation should be the same, whether you entered in the actual year number or somebody else used the 0, 10, 20, 30 scale. Once you plug it in and do your calculation, it should be the same. Okay, Anna? No? Okay. Okay, you could have run your regression differently depending on how you entered the data. So I want the answer to the second question. According to the linear model, what will the egg consumption be, or what was the egg consumption in 1995? Sorry. All right. Okay. Then according to the quadratic model, how did that estimate egg consumption in 1995? See? Okay, and those aren't that different, right? And that's because at the beginning they're both going downward, right? What do you guys think about this question? Which model did you feel was best for interpolation? Within the time they took the data, did you feel that a linear regression or a quadratic regression was the best model to represent that data? Quadratic. Okay, and what are our thoughts to why? Why quadratic? CJ? Okay, so you saw a turn, so you think visually that seems to be the observation that we make. Did anybody look at the r-squared values for them? Yeah? Did a quadratic one have a better r-squared value as well? Okay, so those two things seem to say r-squared. What about the extrapolation factor here? If somebody wanted you to estimate egg consumption beyond the year 2000, but you only have data for the year 2000, okay, first between linear and quadratic, what do you think you would choose? See? Okay, so what happens with the linear one? Yeah, and so but quadratic actually grows faster than linear, okay? So, do you guys think we'll grow faster or slower in our egg consumption? Was the line going downward or upward with its slope? Up or down? Down. So did it cross the x-axis? So eventually they're saying there would be no egg consumption or negative egg consumption, which doesn't make sense. So that kind of eliminates the linear part of it, right? Because it doesn't make sense. Now let me ask you this. You had to choose. So you would choose quadratic because that's the only way to really estimate beyond 2000. However, do you really think that this model would hold up for extrapolation? Do you think if I wanted to see in the year 2500 how much eggs there are, that either of those models is realistic for that? No, right? Maybe we don't know enough about maybe we just don't know enough, or maybe growing that much is ridiculous. How are we even going to produce enough eggs for people to eat that many of them, and that kind of thing? And those are the arguments that you have to think about and think of, because data is real life, right? So it really depends on the situation. Okay. So, how many of you guys can see how this is